we're going to start talking about a different topic now, and that is polynomial regression. Polynomial regression and specifically a quadratic model are very useful in describing a relationship that is not linear. So for instance, if we have, let's say, y and our x variable, and the relationship actually doesn't look like it follows a line, but instead follows sort of a curve, either a concave up or a concave down curve, then it, it is possible that the relationship can be modeled by including what we call a quadratic term. A quadratic term is measured by, or basically represented by, the squared value of the predictor variable x. So for instance, this model, the expected value of y, can now be modeled by the original variable x, but now including the quadratic term. Each one will have its own parameter, and with the parameter mean, actually beta 0 would still be the y-intercept. Beta 1 is a shift parameter, and beta 2 is the rate of curvature. The beta 2 parameter actually models the relationship. If it is actually greater than 0, then the relationship is concave upward. I mean, it looks like this. And if the parameter is less than 0, then it's a concave downward kind of relationship. Um, this is an example of what we call a quadratic model. Polynomial regression is more than that, actually. Polynomial regression can model many different types of relationships. So for instance, let's take a look at an example where we're looking at salary and using experience as a predictor. Let's say experience in months as a predictor, say experience in years as a predictor of salary. Um, Now, this here is what we have been looking so far. This relationship right here of experience versus salary is the kind of relationship that we have been modeling. We have been assuming that that relationship is linear and that linearity is basically captured by the model that we have been actually feeding, which is a linear model. Um, and that is using the estimate of salary and a slope for the variable experience. Now, what happens if the relationship of experience and salary doesn't behave linearly? It just behaves sort of in a nonlinear trend. We can still use a linear model in this case. And the linear model is can be expressed as estimated salary is equal to B0 plus B1 times experience. But by adding that B2, that extra slope, and then putting experience squared, we are still using a linear model. I mean, remember, a linear model is determined by the coefficients, not by the variable. So all of these coefficients are linear, which means that the model would still be a linear model. In that case, this model is what we call a quadratic model because the variable here, experience, is a quadratic term, is to the power of 2. Now, there can be other types of polynomial regression models. For instance, if you happen to know that experience and, let's say, salary behaves sort of like the square root of x, although this could still be modeled by a quadratic model, you could do something like this. You could say salary is equal to b0 plus b1 and then times the square root of experience, and that could be modeled that way. So that still is considered a polynomial regression because um, the um, the the exponents of the predictor variable are sort of expressed in polynomial terms. A relationship of experience and salary that behaves like this might be modeled by something that includes the shift piece here, the quadratic uh, trend, but also adding an extra term to model the cubic expression here. And that actually would be sort of a cubic term. This is also a polynomial regression, and we can add exponents. But just being cognizant that adding more exponents adds more variables and increases the complexity. And it's very likely that if we keep on doing this, then we would be sort of overfeeding the model. And I'll go more over that in depth later. But for the moment, we are mostly in this course exclusively going to focus more in the relationship of quadratic models. Um, with with the hope that most of the relationships that we capture are going to have this sort of relationship. If we let's say have a relationship that looks like this, well, this sort of a square root trend, we could still model it pretty well by with the quadratic term. It's only that the slope of the experience squared is going to be negative, and I mean it sort of will do a sort of a good job in that kind of problem. If the problem is, let's say, it behaves like a cubic trend, it might not do as well, but I mean it sort of will not miss as much. Again, we use sort of that intuition. If you happen to see a relationship that looks like this, you might be okay. I mean, it would be better to just include that extra cubic trend in there. But for now, we will mostly focus on the quadratic kind of relationship. So to do an example on this, I'm just gonna go ahead and talk about the example that we will look at, and then we'll go and do some coding in R. But this is an example called the Boston housing dataset. The easiest way to get that dataset is using the ML bench package in R. This ML bench stands for Machine Learning Benchmark Dataset. If you install that package comes preloaded with the Boston housing dataset. Um, the idea is sort of the same, similar to the estimating the median value of that we saw before, and we just have different variables, different predictors, and it's supposed to be predicting the median value of suburbs in Boston as opposed to California. Um, the one thing to this is a scatter plot matrix of this data set. We are predicting the median value. So we can look at this row, the first, the bottom row here, to look at the relationships. It's difficult to know which variables are have a quadratic relationship with the response. So it takes some practice and it takes some investigation to kind of know which variables you should include uh, terms. I would suggest that when you have a lot of variables, it is almost impossible that that you can create quadratic terms of all of them and start eliminating. It might not make sense to do that. Instead, you would be sort of better off by looking at the relationships and see visually if there is some sort of um, relationship that captures your thoughts of quadratic terms. So in this case, maybe something like this, the crime rate doesn't look like it follows a linear trend. So you might be thinking of maybe including a quadratic trend in that one, maybe the industry variable, um, maybe the lower status, the percentage of lower status in the population. So let's look at this here and focus on that one. This LS stat variable is the percentage of lower status of the population. So if we create a scatter plot just of this variable, here, using it as a predictor, you will see kind of clearly that that doesn't look like a linear regression would do a good job in there. So if we do a regression using median value and getting that y-intercept and the slope using LS stat, this is the kind of parameter estimates that we would have, the y-intercept and then the slope, but this would not do a good job overall. It's the residuals don't look, wouldn't look like they follow a normal distribution. Instead, this looks like the quadratic trend kind of misses these parts really bad here, and then um, overall the residuals wouldn't look like they're constant. So all of these assumptions that we make in regression would probably not be satisfied. Now, if we included a regression using a quadratic trend in there, a quadratic term, we would be looking at the estimate median value using the y-intercept, and now the um, shift parameter on these LSTAT, but now including that extra term, which is the quadratic term. And we want to test if this is significant. The way to do it in R, and we will go over the R code, is to use the I function. And then inside the I function, within the LM function, you can specify any formula you want. So you can actually square, take the square root, make many other types of transformations. And we can see here that this parameter here is the estimate of this is B2, and this parameter is significant. So that means that that quadratic trend actually does make a difference, is statistically significant. It adds. So we can go ahead and increase our predictive, power of the model by including that extra term in there. Um, so this is the model that we would have. This would be the regression, including that quadratic trend, which seems to be a better fit than this original linear model. Okay, so in terms of adding, let's say we want to look at the number of rooms. This is another variable. Again, if we want to take a look at what it means, number of rooms is the average number of rooms per dwelling. So including that extra variable in there, let's suppose that we want to have this new model, and that would be the estimate of median value. We have the y-intercept plus the slope for room plus the slope for LS stat, which is the lowest percentage of lower status in the population, plus another term on the quadratic term on LSTAT and the quadratic trend term on rooms as well. This is the kind of model that we are feeding right here. The only thing that I want to point out is if you include the quadratic trend term in there, it is always advised that you include the original trend, the original term in there. So this is so any lower, you can't have a squared value without the original variable being in there. It's a good practice to include both. Um, so in this case, for this data set, both quadratic trends are significant. One thing that I will note is if this variable is significant, then we would include the original variables, even if their p-values are not significant, just as interactions. In that case, the model would look we have the axis for room, the axis for LSTAT, and the model would sort of look like this. It looks like a plane that is tilted or curved. So that might better capture the relationship between the variables. And that's what we're doing in higher dimensions. So hopefully this makes sense. We're going to go ahead and do an example in R and actually talk about the interpretations and how you would interpret a model that contains a quadratic trend. But hopefully that makes sense to you.